one of the main reasons that differential equations are so important is because it is very convenient to model some real stuff with differential equations, right? So here's an example. So imagine a falling object like a cat jumping from a roof or falling from a high floor, right? So then if we were in vacuum, then in vacuum the equation is very simple, that the acceleration of any object is the gravitational acceleration, right? So the derivative of the speed would be the constant 2.9 meters per second square, and we can solve it by integrating. But of course, on the Earth we have air resistance, and it is natural to assume that the faster the object falls, then the more we have the air resistance, right? So it means that if the object is falling faster, then acceleration becomes smaller, right? And hence we can assume that it follows this model, right? So acceleration of the object, which is the derivative of the speed, is our gravitational acceleration minus something, and the negative term here should be somehow should depend on the speed of the object and should be an increasing function of the speed. So here I'll just assume for simplicity that it is proportional to the speed itself, although maybe especially for fast falling objects it is more accurate to assume that it is proportional to the square, but I'm no physicist, so my point being is that you can take a real-life scenario and make some reasonable assumptions about it, and then translate this real-life scenario into a differential equation, right? So this is called a differential equation. So an equation that relates an unknown function, in this case is the speed as a function of time, to the function itself. And so a very similar example. So imagine a cup of hot coffee. Then of course, as time goes by, the coffee is going to cool down naturally. So and according to Newton's law of cooling, which again I'm not sure if it is true or it is not true, but I think again it is something very reasonable that you can assume that it is just proportional to the temperature difference between the coffee and the ambient temperature in the room, right? So here is what we got. So let me maybe explain. So this is the rate of change of the temperature. Then C is the current temperature, and A0 is the temperature of the ambient air. So C minus A0 would be the air the temperature difference, right? So which is this thing, right? So that's what Newton's law of cooling tells us. Well, and that's just a little problem for you to discuss online, so there will be an online forum here, and you can ask questions, and you can also discuss topics related to our course. For instance, here is a problem that I think is nice, so you can try to figure out how to solve it using the theory of differential equations. Alright, my next example is about population growth. So imagine bacteria, right? So then population growth rate, so the rate of change of the population. So so here population is P of t, right? So let me highlight it. So by P of t I mean that this P of t is really maybe the total mass of bacteria, right? So it changes continuously. Total mass of bacteria. I'm sorry. Then the more bacteria we have, the faster they multiply, right? So mathematically, the rate of change of the total mass of bacteria is proportional to the mass itself. But of course, clearly it cannot go on forever, right? So they only have a limited amount of food. So and then at some point they will run out of food and they will have to maybe eat each other, or I don't know, or just die younger, whatever. And the more differential equations that can take this into account, it looks like this. So let me explain why. So imagine that if p is very small, right? So if p is, I will write much smaller than k. So if p is much smaller than k, then p over k is nearly 0, and this term disappears. But if this term disappears, then the whole equation here just becomes the original equation, dp dt equals rp. So it means that if p is very small, then the equation that I just wrote down is actually very much like the equation that tells us that the growth rate is just proportional to the population. Alright, but imagine now that p is just a little bit closer, a little bit smaller than k, right? So imagine that p is almost equal to k, just a little bit smaller. Then p over k is going to be approximately 1. And then 1 minus p over k is going to be 0. So here, this whole right-hand side is 0. So in other words, the equation that we just wrote down tells us that if p is approximately equal to k, then the rate of change of bacteria is almost 0, which means that the population is almost constant. Right? So in other words, what we have described here is that in the beginning, the rate of change of population of bacteria is proportional to the population itself, and it grows very quickly. But then eventually it slows down. So the more p grows, then the smaller this term becomes, 1 minus p over k. And then when the population almost reaches this number k, then the rate of change is almost 0, so which means that the population doesn't really grow any further, right? And therefore this whole equation is probably, I'm not sure how realistic it is again, but I think it is very reasonable, so to say. Okay, then you can try to the third example, or maybe sorry, another kind of an extra layer in the third example is just for your information that at least as far as my knowledge, that the historical growth of the human population, it fits into a different differential equation. So instead of being proportional to the population itself, the rate of change is proportional to the square of the population. Yeah, and here we have a little bit kind of a strange effect that I suggest that you try to think about and discuss online, is that unlike the previous example with bacteria, so imagine that if I didn't have this term, if I didn't have this square, right? So imagine that I didn't have it. If it's just dp dt equals kp, then although it would mean that the population just grows exponentially and is not limited to by any number, but at least theoretically it can grow exponentially, so that there is no even theoretical limit to the population. But if you put the square here, then it is impossible even theoretically. So although somehow historically it seems to be a better better fit, but that is impossible not even in practice but even in theory. And my question is why? Can you try to figure it out?